Let's start out with a quiz. And the quiz is the following. I have some little intuition about this quiz. The quiz is A, if you're more likely to look things up on Facebook, or B, if you're more likely to look on Piazza, and C, if it's about equal, and D, if neither. A is Facebook, B, Piazza.
Is it for this class or for any?
Well, just, I'm trying to figure out what's going on in this classroom right now. And I have a hunch. So this was Facebook, Piazza, equal, something else. Okay, that's for this. Okay, that's for this class. Oh, you have, okay. What's the other option? Other option? Another option. Okay, how about separate from this class? Just in general, would you feel more comfortable with Facebook or Piazza? Like if I just said, let's cancel the Piazza page, we're going to do it all on Facebook instead, would you prefer that? What? What's that? What were you thinking? Okay, just as a matter of preference, running the course, we're putting all the news and chit chat on Piazza. What if we instead did that all in Facebook? You think that would be better? Facebook is better? Piazza's better? You're not sure? Okay, but somehow somebody will tell me there's some communication going on between people in this class, and I don't really know what it is, but I hope you're making good use of this communication. Okay, now another thing. There's been a little chat about on the Piazza page about having another makeup prelim, and I just want to hear what you guys think about this idea. I'm not making an offer, I'm just asking for opinions. So the suggestion a student made is that we give another makeup prelim, and people can take it, and it's completely optional, and the grades only count if you do better on the makeup prelim than you did on the other 3 prelims in the final exam and stuff like that. That's the idea somebody suggested. Is the idea clear?
What was the subject? Would it focus on one?
Let's say it focused on the course up to a week before the date of that prelim, whenever it was. Okay. So it's like, it would be like the makeup prelim, which we already have, but now we have it to replace the prelim if you didn't take it. This would be, even if you did take the prelims, you could take it to substitute in lower grades, to substitute in other grades. Okay, the idea clear? Okay. Now I think this is a bad idea, so I'm going to tell you why I think it's a bad idea. Because let's say we did that, let's compare it to something else, which is I just say, oh, sorry, there's a 4th prelim this semester, but instead of dropping the lowest 3, it's dropping the lowest 6. That second thing I said is identical to the first, as far as I can tell. Does anybody see a difference between the two? Now, there could be the word optional in front of one and required in front of the other, but the effect is the same. Does anybody see that they're any different? Yes? What does the word optional mean? What does have to mean? Is class optional? What? In a sense, everything's optional, right? You don't have to do anything. The only thing we hold over you here is if you cheat, then we expel you or get you in trouble. If you do badly or skip something, you get a lower grade. But that's true for the prelim 2 also, already. Prelim 2 only helps you if you do better on it. Do you see or no? You have any trouble seeing the difference? The word optional has no meaning. It's just a matter of what happens to your grade. Unless you care deeply about what I say and I say it's required that you read page 362, the second paragraph, and memorize it. And what do I mean it's required? If I don't say it's likely to be on the final exam, the words don't have meaning. All I have to hold over you is grades, right? I strongly advise or something, but the word required and optional don't have meaning. Okay, so now given that, how many people would like there to be, I'm not making an offer. How many people would like there to be a fourth, yes?
I have a question about your argument why it wouldn't be good. You said it's the same thing as just having
Another prelim and drop 3 more lower grades.
So is there any negative effect?
Yes, yes, because let's just assume that every test you take, first of all, let's assume you're in here for the grades and not for education, which I know is not true for any of you, but let's just say that was true, and you're trying to get a good grade, and you're not worried about your education. Let's just say your test scores are random. If you have 9 test scores, and you get to drop the lowest 3, or you have 12 and you get to drop the lowest 3, on average, if you take 12, your net average will be higher, or 12 and drop the lowest 6. The more you take, the more there's some chance that your grade goes up. So that it's not saying, oh, it only helps if you do better. It's not a meaningful statement. On average, it helps everybody if they take that test.
So what's the problem with anyone getting that?
What's the problem with having that test?
Yeah.
Well, then we could.
It helps everyone.
It helps everyone who takes it, but then it adds a 4th test to the semester. Let's do it again. Should we start the whole semester and have 4 prelims instead of 3? How about 5, 7, 9? Does anybody understand or not understand? Yes?
Also, if it helps everyone and the class is curved, and then you bring everyone's scores up, then you're determining.
No, all systems, whatever they are, you compare System A and System B, on average, some students will do better by System A and some by System B. So it's not that they exactly help everybody the same. It's not like adding 10 points to everybody's score in the course. It's not the same as that. On average, for the whole class, it has no effect, but for any individual, they'll go up or down by one system or another. That's why I think I might have told you this at the beginning of the semester. Did I tell you about Professor Rand was threatened to be sued?
What?
I told you that story? Okay, so Professor Rand had a scheme where he had dropped the lowest, something like we have in this class, and a student came in at the end of the semester, I think it was a student's father, a lawyer, came in and said, my son or daughter or whoever did better than the mean on every single part of this class, yet got lower than the mean in the final grade. That's not fair. But that's a consequence of a drop the lowest scheme. As people who are erratic, 2 people have the same average, the one who's erratic gets a higher score in the end. So any system which you say, oh, it doesn't hurt you, it doesn't help you, is not true. Every score gives different people different numbers, every system, and a drop the lowest system tends to reward relatively erratic people over steady people. That's the way that system works. Now, I use it because most students sort of like the safety net, but you can't say, oh, it's equally fair to everybody, because it's not. If you're a totally even performer, it's worse for you. Yes? No? Now, considering just my impression of Cornell students, of which you are some, considering how much people care about grades, I'm always surprised at how little people have thought these things through. So I dedicate, therefore, 10 whole minutes of lecture to this topic. Okay, now I want to have a vote on this. How many people would prefer to have an extra makeup exam which only counts if you score better on it? Yes? No? Don't care? Still don't understand? Okay, that's what I thought, and that's what I think is reasonable. But I think if I pose the question a different way, oh, it only helps you if you do the exam. Do you mind if other people take the exam? Maybe I could have conned you into voting A, but I shouldn't have been able to. Okay, yes?
It seems like we already have that scheme that you're proposing built in, since we have one more prelim and those other classes and give them drop score.
We already have it, right? We already went from 2 up to 3. We built that in. So it's just 3 up to 4, 4 up to 5, 5 up to 6. We could have 27 prelims and only the best 25 count. I mean, the best 2 count. Which is not unreasonable if we had at the beginning. It's not like that's a crazy idea. You only your best work counts. It's reasonable. Okay, I want to go on to the problem of balance, and you guys have dealt with this. By the way, in terms of the psychological effect of this tight room, this works, by the way. This is nicer than everybody being all over the place. It's fine with me. And it's nice to see so many people here today, too. Okay, so there's the pendulum. You've dealt with the pendulum. You know how it works. You can deal with it like this. If I have an inverted pendulum and I just put a hinge here, there's a stone inside here. The third grader in me can't help but do this. Did anybody see where it went? It's in my mouth. The whole thing is plugged. Okay. Okay, so we can also do the inverted pendulum. And it falls over like this. And you know how to write the equations for this. It's theta double dot is equal to minus sine theta with a constant in front, or theta double dot is plus sine theta if we measure from here. Or if we use the same definition of theta, it's the same equation here as here, but near this position we get, it's at 180 degrees as we get this unstable motion. What happens if I move the base around? Well, if I move the base around just the right way, I can balance this thing. And the question is, can we figure out that balance? Well, how do you balance it? Is you move your hand around. What if I just move my hand around? Let's see, I was going like this, and I just move my hand back and forth like this and try to balance it. Does it balance? No, it doesn't. So I have to move my hand around just the right way. What's just the right way? Well, you can look at my hand and make a movie of it, and then we can put the pendulum on top. So my hand moved just like this, and I put the pendulum on top, and I move my hand around just like that. No, that doesn't work either. To balance it, you have to move it in response to what you see. So that idea of all this dirt coming. This is leftover from my wife's PhD thesis, which was 20 years ago, found in the basement, which was making a cage to watch wasps lay eggs and butterfly larvae. Okay, so where was I? We're trying. You have to move in response in just the right way. How to do that is what you'll learn in later courses in controls, linear systems and controls. Our goal here is to be able to write the equations so that you can set up that controls problem. In fact, it's an experiment you'll do next year is exactly this problem, setting up this controls problem that's set up in the second floor of Upson over there. So what we'd like to do is figure out, if we knew how the hand was moving, how does this move? And then a later problem, which we're not going to do, is figure out how to move it in a stabilizing way. One could ask the question, is there some special way of moving this so that you don't have to use what's called feedback, which is move in response to what you see, but is there some special pattern of motion which will balance this? Does anybody have an opinion on that question? Okay, well, here's this funny machine. And this machine is a Scotch yoke. So what happens is there's a little round thing, which is eccentric, moving between two plates. And so these two plates move up and down in a sinusoidal motion. Who has seen this demo before? So this moves up and down in a sinusoidal motion. And this thing is a stick. It's an inverted pendulum. And the question is, can I balance it just by moving that up and down? So we try it faster and faster and faster. There's no feedback, it's just bouncing up and down. Now the theory of that we can't do here. But what we can do is get the differential equations write them in MATLAB, simulate them in MATLAB, and see if MATLAB agrees that what you see here follows from the laws of mechanics. Okay, so that's what I want to do. Now, I'm going to put my computer away for a little bit, and then I'm going to bring it back again. Okay, so we're going to have some motor down here which excites this thing in a sinusoidal way so that this thing goes up and down according to sine omega t. And this thing maybe has some length L, and we can measure the angle one way or another. Let's say we measure the angle here from the x-axis, just so that we can use our polar coordinate formulas without thinking about it. By doing that, we're going to make it so the pendulum equation is going to have a cosine theta in it instead of a sine, but we still get video blank. I tried that. It says video blank. Did I get rid of it? We have, say, some mass here. We have g like this, and we would like to figure out how this thing moves. So how are we going to do that is we're going to use a free body diagram. And even now that the course is getting so complicated and all the kinematics is complicated, it's still true that when you use the laws of mechanics, they're based on a free body diagram. So don't forget that. You have to still draw free body diagrams if you're going to be using the laws of mechanics, if it's more than kinematics. Everybody got straight the word kinematics and kinetics now at this point? Anybody want me to say what it is? Raise your hand. Okay, kinematics is the geometry of motion. It has nothing to do with the laws of mechanics. Well, it has something to do with it. You use it when you're doing mechanics, but it does not engage the laws of mechanics. It's just about geometry and motion. The 5-term acceleration formula, the 3-term velocity formula, the polar coordinate velocity acceleration formulas, the path coordinate formulas, all of those are kinematics. As opposed to kinetics, mechanics, where you write the laws of motion, you use linear momentum balance or angular momentum balance. You use the kinematics to calculate the accelerations in order to put into the mechanics. Okay, so for this problem, we can draw a free body diagram. There are various things we could draw free body diagrams of. We could draw the whole stick or just the mass. To keep this problem simple, let me just do, well, I'll do the whole stick. So we draw a free body diagram of the whole stick. To keep it simple, just so I don't have to write so much on the blackboard, I've assumed that this part of the stick is massless. That's not essential. It just saves a few lines of calculation. And we have some force here, and we have some force here, and we have mg here. We could put minus mgj. I don't have to call these things anything because I'm going to finesse having to find them because I'll use angular momentum balance about this point. And in case anybody wants to know, over here on the side I've got this length and I've got this angle measured counterclockwise from the plus x-axis. Okay, so in order to get the equations of motion, what I'm going to do is I'm going to use angular momentum balance relative to the point O prime. Now the point O prime is an accelerating point, so we cannot calculate angular momentum balance by first calculating angular momentum relative to the moving point O and then differentiating. Rather, we use the acceleration formulas for rate of change of angular momentum. So we write them like this. The sum of moments relative to O prime is equal to H dot relative to O prime. And what goes into these? Well, we have, in this case, we have this force pushing down. And what is that? That's mg, with this particular theta, is mgl cosine theta minus mgl cosine theta k. And I could have worked that all out with cross products. That would have been the position of, let's call this point P, of P with respect to O prime crossed with minus mgj. But I can do that one in my head at this point in the class, and I think you can too. And then on the right-hand side, we have the position of P with respect to O prime crossed with the mass times the acceleration of P. And now we mean the acceleration relative to some fixed frame F. So what we can do in this picture is we can put an x prime and a y prime, and we can call this some moving frame B. And down here on the side, we have some fixed frame F. And where the origin is of this thing doesn't really matter because we're not going to be using those coordinates at all. So these are the equations of motion. One thing to observe, this is a little advanced aside, I'm just going to say it for those of you who like such things, is that on the left-hand side we have r cross the gravity force, and on the right-hand side we have r cross ma. Let me go another step, sorry, before I point this out. So then we have our minus mgl cosine theta k is equal to the position of P with respect to O prime crossed with the acceleration. And the acceleration I can write as two terms. One is the acceleration of O prime with respect to O, and the other is plus the other four terms in the five-term acceleration formula. Now in this particular case, we get the acceleration of P with respect to this moving frame. And we have no other terms because the moving frame is not rotating. All the other terms have to do with the rotation of the moving frame. So we have here plus 0, plus 0, plus 0. Now let me make my comment. If this acceleration is 0, then we have, there's a mass missing from this whole expression. If this term is 0, the acceleration of the frame, then this looks exactly like we would have had for a stationary pendulum. And it is exactly the same. If that motor on that thing is not turning, we get exactly the inverted pendulum equations. Any questions about that? The interesting thing, or it was interesting to lots of people for many hundreds of years, is that this term here, these first pair of terms, sits in exactly the same place as this term here. What do I mean the same place? It looks just like it. It's got this crossed with this. And the way it works out is for any mechanics problem, no matter how complicated it is, whether it's point masses or rigid objects, this correction term always has this form for all the different parts and can always be moved to the left-hand side and mixed with this term. What that says is this famous thing that you heard in high school as sort of a deep idea, and it is a deep idea, but it's a theorem in mechanics, which is that you cannot tell the difference between being in an accelerating reference frame and being in a gravity field. So you hear that usually in the context of general relativity, which none of us understand unless you're different from me. But it's not actually a consequence of general relativity. It's not actually something Einstein discovered. It's a theorem in classical mechanics that nothing in the classical mechanics equations can distinguish an accelerating reference frame from a gravity field. Rotating, yes, but accelerating, no. And that's true for this problem and for all problems. Now Einstein took that and said, let's make that a postulate for all of physics, and then that invented general relativity from that. But he started with this mechanics theorem, of which this is just a specific example. Okay, so now on the right-hand side here, we get the position of P with respect to O prime crossed with, and now we have the acceleration of O prime with respect to O. Well, this is going up and down in the y direction. We differentiate twice, and so that just turns into a minus d omega 0 squared sine omega 0 t j. And then we have plus the acceleration of p with respect to b, and then we can say that's equal to, well, we can just use the polar coordinate formulas. So over here we could put an ER and an E theta, and we can imagine that those are part of this moving frame. So we get plus something times ER plus something times E theta. And what do we get times ER? The radial term is minus L theta dot squared. And what do we get for E theta is L theta double dot. And there are two more terms, both of which are 0, because this is a circular motion problem. Circular motion with respect to the moving frame. Okay, so now we want to work this out. We have minus mgl cosine theta k is equal to, and now we have this cross product, but this term here, r, p with respect to O prime, is L E sub r. That goes in there, and that goes in there. We still have our m multiplying this whole thing. There's an m there. And we have to do all these cross products. So we have here an L times something. And what do we have? We have an ER crossed with J. ER crossed with J, that's big. ER crossed with J is has to do with how perpendicular this is, and that's 0 when theta is big, so that looks like a cosine theta. So we have an L cosine theta, and then that gets multiplied by minus d omega 0 squared sine omega 0 t, and that's in the k direction. That's that first cross product of r of p with respect to O prime crossed with where did I put it? This minus d omega squared sine omega t j. Everything's going to get multiplied by m on the outside. Okay, is that okay for the first term? Then the other terms are easy, because ER crossed with ER is 0. ER crossed with E theta is just k. So we just get this L squared theta double dot k. And this whole thing gets multiplied by m. Any problems with that? Now we take this whole expression and we take the dot product of both sides with k, and we get out that theta double dot is equal to, and what we get is a cosine theta, and then we get a g with a minus sign, and then we get a minus d omega 0 squared sine omega 0 t, and this is all over L. So what we get here is that we get a g plus this term, which is the vertical acceleration of point O prime. So this is the same as we would get as the pendulum equation. It's got a cosine instead of a sine because we measured our angle from the horizontal instead of the vertical. But we get the pendulum equation with g replaced by g plus minus d omega 0 squared sine omega 0 t. And all of this is just the acceleration of O prime with respect to O. So we get back that result, which we expected on general principles, which is that we cannot distinguish between being in an accelerating frame and having an altered gravity field. Now we can put this in MATLAB and see if the equations agree. So let me just show you how this goes in MATLAB briefly. Any questions about what's, maybe just stare at the blackboard a little bit, correct any sign errors that I made, things like that. Yes? You want this term to be a plus? Okay, we can track it through. I'm going to do it by thinking instead of by algebra. Okay, if you just excuse me for a second. Next to g should be the vertical acceleration. So we should add to g the vertical acceleration. And this is a minus g here. And this was a, so it should be minus g plus the vertical acceleration. But the vertical acceleration was minus this thing, so that should be a plus. Okay. And I assume the algebra will be consistent with that. Yes? I can try. It says pendulum equation with G, R-E-P-L-A-C-E-D, replaced by G plus the acceleration of O prime with respect to O, which is this minus d omega 0 squared sine omega 0 t. Okay, so now that we've got that differential equation, it's simple enough to put it into MATLAB. This is the kind of thing we did lots of times earlier in the semester, and you've done since then, hopefully, a bunch of times, but I have not done in lecture because you asked me not to, but now I'm going to. Whoa! I didn't mean that. Board lights off. Hey, come on, man. Board lights off. Podium lights off. Send to center display. Let's see, while we're waiting for that. Send to center display. Laptop. Send to center display. Finally. Okay. The demonstration I showed you before, let me show it to you again with a video so you can perhaps see it better than you can see it. So this is about a 1-minute long video, and it's just showing the demonstration. Here's showing that it's a pendulum. Then you shake it up and down. Now it looks like it's shaking slowly here, but that's a stroboscope effect because the frequency of the camera is close to the frequency of the oscillation. So that slow motion aspect on the bottom is not how fast it's oscillating. It's oscillating at something like 60 hertz, which matches the frame rate of this camera. Then here it is in slow motion. So here's what happens if you knock it sideways in slow motion. And I advertise to you that to understand dynamics, you should be turning on your internal slow motion video simulator often for dynamics problems. Why is dynamics hard? Is because it happens so fast. Why does dynamics have to happen fast? Because when it's slow, friction wins. Okay, and here's the thing balancing. This is now at high speed, but shown in a slow motion video. And here's what happens when you knock it sideways when it's balanced like that. And then it pops back up. Slowly. Okay. Any questions about this video? Yes? Say again? No, it would not feel like the 0G. The pendulum wants to align with the vertical. If we just turned off gravity or we went into the space station, which, by the way, you call weightless, which is like 0G. Why is that? It's because it's the centripetal acceleration balances the actual gravity force. And because mechanics can't tell the difference, if you have the right acceleration to match the gravity force, it feels weightless. That's how it feels when you're, jump off a diving board. It feels weightless. It's not actually weightless. It's that there's an acceleration which cancels the gravity, so you can't perceive either one. If it was weightless, this would be neutral in every position. And if I gave it a knock, it would go at constant angular velocity. So this wants to align with the direction of the shaking. Okay?
Could you align it at a specific angle?
If I shook it that way, in a weightless environment, it wants to line up with the shaking. That's the way the solution of the equation works out. So if I shake vertically, it wants to align that way, or it wants to align this way. If I tip the motor, it wants to line up with the crooked direction. And even that effect shows up, even if there is gravity, then you're competing with gravity, but the same thing is true here. Let me show it to you. So what you were supposed to see is that the shaking force was trying to align it with the shaking force. Gravity was trying to tip it. The more I tipped it, the shaking was trying to keep it aligned this way. Gravity was trying to knock it over. When I tipped it enough, eventually it leaned over. Could you see that? Who wants to see it again? Okay. Who asked the question? Are you happy with that answer? Okay, now let's go to the MATLAB world. And here's this simulation. And I'm not going to go through the details, and I'm not going to do live programming. But here is in the basic setup. I set this up to do fast simulation or slow simulation, so it's a lot of bells and whistles. The key to the whole thing is this command, which says do the simulation. What is the simulation? That happens in the right-hand side here. The right-hand side here is just looks like the pendulum equation, except I left real gravity off. So in order to show this aligning effect most clearly, I shook this thing in outer space to show that it would line up with the direction of shaking. So it just has this sine theta, where theta itself is changing in time, and then I have this force, this synthetic force, which is meant to be the coefficient of that equation, and the coefficient of that equation is here. I could add a g to this if I wanted. So this is the coefficient of sine in the equations of motion. Then I have a bunch of graphic stuff because I make this a fancy graphics thing. This is the kind of thing that if you like to waste time making pretty graphics, you can do these things. Okay, so I get out of this this simulation in slow motion, and this is meant to be explaining why this thing works. So I'm going to try to explain to you why this thing works. That's sort of distorted. It's not supposed to be distorted. There we go. Okay, so the question is, why does this work? So now I'm going to try to give you an intuitive explanation for why this thing works. There's a point mass up here at the end. Imagine that point mass. And I'm going to move this up and down. And we're going to turn off gravity so we can just try to see if there's a force that tends to line this up. Now, the force of this massless rod is always along the rod. Now, if we did the equations with inertia here, the force wouldn't be along the rod, but the equations are the same, so presumably the intuition should work out the same. But the simple intuitive explanation only works if we put a point mass at the end and had a massless rod. Okay, so there's a force along the rod. It's pushing this thing away, and then it's pulling it back. So here's the mass. It's being pushed away, pulled back. Pushed away, pulled back. But now look at the angle of this rod. When it's pushing away, the angle is somewhat more vertical than when it's pulling back, because this end of the rod is going up and this end of the rod is going out. So the angle changes slightly, and in the pulling back phase the force is in this direction, in the pushing out phase it's in this direction. So it pushes out this way and then pulls back that way. Those two directions are a little bit different, so there's a net force in that direction. And you can see that in this video a little bit. So this is just a close-up of the end of the motion. So what you see is that red line, the direction just changes slightly, because the end, which is off on the bottom left, you don't see. The angle is changing. It's more vertical now, and relatively more horizontal, and relatively more vertical. And down here is the pushing part. Up here is the pulling part. And if you push in that direction and then pull in that direction, the net is a small force in that direction. And that's the physical explanation for the stabilizing effect, which you cannot read in any book, as far as I know. The only place you can learn that so far is in a lecture from me. So this is it's a famous problem, but intuitive explanations for it are really lacking. And so I'm proud of that thing I just told you. It took me a long time to think up. Okay. Sounds simple after you hear it, I suppose. Any questions about this example? Let me just, to show you why these things are interesting, maybe, is this funny video, which I'm going to show you. Let me describe the video to you. Here's this balancing problem when you can balance the stick by going like this. Another way to balance the stick is to have a motor at the bottom, and when it tips this way, you correct it this way. When it tips this way, you correct it this way. I could just hold it solidly here, right? But let's say I don't want to just be so tense about it. I only want to use the torques I need. So I just hold it in a gentle way, and I look at it, and when it's tipped one way, I tip it back the other way, tip one way, and I just do this very gentle thing, and I can balance it. If I close my eyes, I can't do that anymore. If I hold it in this gentle way, and I try to balance it with my eyes closed, I can't. I need the feedback. I need to look at it if I'm going to just use my fingers in a gentle way, so I make corrections. These corrections, applying torques here, are exactly analogous, if you work out the equations, to applying an acceleration here. I apply corrective motion. By the way, this is how a bicycle balances too. When you fall one side, you steer and bring the wheels back underneath. You fall this way, you steer back underneath. So I try to balance like this. And the question is do you have any experience in your life with doing this control problem? Okay, now this is an amazing thing. I would like everybody to stand up. Just everybody stand up. Now I want you to stand as still as you can stand. Just stand as still as you can possibly stand. You're a super yogi. Now the question is, when you stand still like that, what are you doing? You could think, oh, well, my feet are flat. I'm balanced like a 2x4 balanced on its end. Because my feet are flat, I'm just balanced there. For that to be true, your ankle joints would have to be locked. But if you're standing very still, you will feel that your ankle joints are not locked, and it turns out that your muscles are not stiff enough to balance you when you're standing. When you stand perfectly still, you are actively balancing exactly the way I just showed you with this stick. You are using your ankle muscles. When you fall forward, you're pushing to lean back. When you fall back, you're pushing to lean forward. And you are doing that constantly as you stand still. So just everybody, I want to shut up, and I want you just to have 10 seconds to concentrate on that, and then I'm going to show you a video. Okay, just out of curiosity, who could feel themselves actually doing that feedback? It's hard to feel it, and it's sort of you don't believe you're doing it. But now let me show you this amazing video. Okay, this is a video of somebody standing up, just like you, a normal, healthy person, and there are markers on their body, and this is showing their body moving as they're standing up. So this is exactly the experiment you just did, but this is with video markers. Okay, so now, how can I do this that will be really effective? So there's the person standing just like you were, and they're moving at the top about a centimeter, something like that. Now the other video, which I'm going to unbury, is exactly the same video, but they've exaggerated the horizontal motion by a factor of 10. In this case, horizontal in this plot is forward and backward for a person standing. And in doing that, the positions of the markers got messed up. So don't look at where the markers are, because when they exaggerated by a factor of 10, they had to put some reference point, and they didn't do that in a very consistent way. But there's markers on the head, the shoulders, the hip, the knee, the ankle, and they exaggerate it by a factor of 10. And this is, for sure, what you looked like when you just did this experiment. That's what standing still is. I think they should have exaggerated by a factor of 30, because what you see if you did it by a factor of 30 is that when you're standing still, just imagine, I know this is none of you, but one of your friends or one of your friends' friends is drunk, and you ask them to stand still. They go, I'm not drunk, I can stand up. But that's what you're doing all the time when you're standing still, just less by a factor of 30. Right, so that's sort of an amazing thing. So that means you have these feedback loops, and people do all kinds of elaborate experiments to try to figure out what is the nature of the control that people do when they do that standing. So they do it. They make you blindfold and see if you can do it, and it changes the way you balance a little bit. They numb your ankles so you can't feel your ankles. They put you on a platform where the platform moves back and forth as you fall, so you can't measure your ankle rotation. They put you in a room, and the room is a synthetic room, and they make the whole room tip with you when you're doing your motions so that you can't perceive your balance by it disrupts the vision. They do it with people who have broken inner ears. Maybe one or two of you have broken inner ears, and each person sort of balances differently depending on what perception or actuation they have available to them. Okay, any questions about this or the example? As far as the courses goes, the main thing you're supposed to learn is how to get to the equations of motion from the physical description, how to set that up on the computer and solve it on the computer. You had a question?
What if you purposely lean forward?
Say again?
Lean forward on purpose and you try to balance that way?
You could, well, your feet are so big. You are stuck, you should be able to reason this out, you are stuck balancing with your center of mass somewhere between your heel and your toes. You can't balance anywhere else. How big a range is that? If I try to move my center of mass, what's the farthest point back I can balance? What's the farthest point forward I can balance? That distance is probably about this big, which is sort of the effective distance I have to work with on my feet. I can't go all the way to the back of my heel, and I can't go all the, my toes aren't strong enough. So you can only balance in this range, and I can balance here, and I can balance here, but I can't balance forward of that because that would require suction at my heel, and the ground doesn't suck. Okay. End of class.